Hello students, today we are going to discuss about a topic on electronic devices. The topic is extrinsic semiconductors. So, why we are actually going to learn about extrinsic semiconductors? Okay, the simple reason is that we are not satisfied with the intrinsic semiconductors, their performance and the amount of current that it is capable of, the amount of conductivity it has. So those are not satisfactory, and that is the reason why we are discussing about extrinsic semiconductors, and majorly used silicon semiconductors or germanium semiconductor, whatever it is. Okay, majorly used are nothing but extrinsic semiconductors. We are not generally going to use intrinsic semiconductors unless until we specifically require intrinsic. So we know that why we actually use semiconductors over the top of conductors in the case of electronics. Okay, the reason is that in the case of semiconductors, we can have the control over the flow of charge carriers that is not possible in the case of metals. The reason is very simple, because the metals have a huge number of charge carriers, and when you have something which is very huge, it becomes very difficult to control it. And we know that in our electronics industry, we require to have a control over the flow of charge carriers, and therefore we have selected the semiconductors. But the semiconductors in that pure state, which we call as the intrinsic semiconductors, are not going to give us a satisfactory amount of conductivity, and thereby it is not going to give us satisfactory amount of current. And therefore we are forced to introduce some impurities into a particular material, which is semiconductors, so that its conductivity can be improved. So when you are adding some impurities with the purpose of increasing the conductivity, and that is what we call as extrinsic semiconductors. So we are going to have two types of, majorly it can be classified as two types of semiconductors. One is the N-type semiconductor, the other is a P-type semiconductor. One is the N-type. N means negative. When the negative charge carriers are going to dominate over the positive charge carriers, then we call it as an N-type semiconductor. And similarly, we can also have a P-type semiconductor. Now what is a P-type semiconductor? P means positive. So when the positive charge, the positive carrier charge is going to dominate over the negative carrier charge, that is what we call as a P-type semiconductor. So extrinsic semiconductor is basically because of adding impurities. When you introduce or add impurities, and now impurities can be of two types. One is what we call as dopants. The other are contaminants. We are going to have two types of impurities. Okay, one is a dopant, the other is a contaminant. We generally use dopant, not contaminant. So what is the meaning of a contaminant here? Both are impurities, but one is a desired impurity, the other is an undesired impurity. Dopants are those impurities which are going to help us to improve the conductivity of the material, whereas contaminants are just impurities which are not desirable. So when they are not desirable, they are not going to be useful for us. So whenever we are talking about an extrinsic semiconductors, we are going to discuss about the impurities which we call as dopants. Okay, so dopants are those impurities which are going to improve the conductivity of the material, which we call as a extrinsic semiconductor. So here we are going to prefer the dopants, not the contaminants. Now, based on the types of dopants that we can have, we can classify the materials as an N-type material and a P-type material. So N-type semiconductor or a P-type semiconductor. As we have already discussed, in the case of N-type, electrons are going to be the majority carriers, because N is nothing but negative, electron is a negative charge. So electrons are going to be the majority carriers and holes are going to be the minority in the case of N-type semiconductor. Similarly, in the case of P-type, holes are going to be the majority carriers and the electrons are going to be the minority carriers. So after doping the impurities, after that the resultant semiconductors can be classified as N-type and P-type. So when electrons are dominant, we call as N-type. When the holes are dominant, we call as a P-type material. Now, in order to have a N-type material, we are going to use a pentavalent impurity or a fifth A group elements. So if you want to have an N-type semiconductor, then definitely you are going to add the fifth A group element, and similarly here you are going to use a trivalent impurity or a third A group element. So the reason why we call here as a pentavalent, here as a trivalent, is because we know that in the case of a 5A group element, generally the valency of those elements is 5. That is why we call it as a pentavalent. And similarly here, in the case of a third A group elements, here the valency is nothing but the number of electrons which are present in the valence orbit of a particular atom. So in the case of a third A group elements, the valency is equal to 3. That is why we call it also as a trivalent impurity. So here it is pentavalent impurity and here it is a trivalent impurity. Now what are the examples of pentavalent and trivalent? I'll write the examples here. So examples are nitrogen, phosphorus, arsenic, antimony and bismuth. So here the examples of the trivalent impurity are boron, aluminum, gallium, indium. Okay, so these are the third A group elements and these are the fifth A group elements that we are going to dope so that we can have a desired type of semiconductor, extrinsic semiconductor. Now we know that, see here, there is one important point that we have to discuss, is that we know that we are doping here, we are introducing the impurities. Now what are the level of impurities that we want to introduce? Is it going to be very high, or is it going to be very less, or it is going to be moderate? Because when we have decided that you're going to have an extrinsic type of semiconductor, then you have to also decide what is the amount of impurity that you're going to introduce into the material. Is it less, is it moderate, or is it very high? So based on the number of impurities that you are introducing, now what is the difference between having the different types or levels of impurities is that as the level of impurities are going to increase, and similarly the material is also going to increase its conductivity. If the level of doping is very high, or if you are introducing so much amount of impurities, then in such a case the material is almost going to have a metallic characteristic. Now, what I mean by metallic characteristic here is that the conductivity of a material gets very high when the number of impurities are too high. And we know that as a consequence, it gets a little bit difficult to have a control over the flow of charge carriers, because when you have a number of charge carriers too high, then it becomes very difficult to control. So definitely there are both pros and cons of discussing about the amount or level of impurity that we are going to introduce. But we discuss generally about three types of level of impurities. So when I am talking about level of doping, when I discuss about level of doping, there are basically three levels of doping. One is what we call as a high level doping. The second is a moderate level doping. The third one is a low level doping. And we know that based on the concept of mole and Avogadro number, we can actually calculate the number of semiconductor atoms that we have in a particular volume, or simply what we call as a density of atoms of silicon or germanium, whatever type of semiconductor that you have selected. For example, if I have selected silicon, then in such a case I can calculate the density of atoms that I can have in a particular volume. Okay, so that value is equal to N is equal to 5 into 10 power 22 atoms per centimeter cube. This is a fixed value. Okay, this is based on the concept of mole and Avogadro number. We can easily calculate, okay, the number of atoms or the density of atoms which are present in a particular volume. Okay, that is equal to the 5 into 10 power 22 atoms per centimeter cube of silicon. Okay, so now why we are discussing about this one is because now to which extent you are introducing the impurities. So here we write it in terms of 1 is to 10 power 3 to 10 power 4. What I mean to say here is that for every 10 power 3 silicon atoms, I am introducing one impurity. Or for every 10 power 4 silicon atoms, I am introducing one impurity. That is the meaning of writing 1 is to 10 power 3. So I am going to introduce one impurity for every 10 power 3 or 10 power 4 silicon atoms. That is what we call as a high level doping. That is what we call as a high level doping. In the case of a moderate level doping, it's going to be 1 is to 10 power 5 to 10 power 8. So for every 10 power 5 to 10 power 8 number of silicon atoms, if you are adding one impurity, that is what we call as a moderate doping. And similarly, you can have a low level doping where it is more than that. So 1 is to 10 power 9 to 10 power 11. But generally in practical cases, generally we are going to have minimum level of doping is equal to 1 is to 10 power 11. Okay, so 1 is to 10 power 9 to 10 power 11 number of silicon atoms, you are adding one impurity. That is what we call as a low level doping. So we are just classifying it as a high level doping, a moderate amount of doping, and a low level doping. Okay, it can be either N-type or P-type doping. Okay, but this is the level of doping. Now what we are going to do is that we are going to understand how a particular material is going to behave, okay, after doping. For that, we are just graphically representing what is going to happen after doping. First of all, we are going to discuss about an N-type semiconductor. It means that into an intrinsic, okay, if the semiconductor that we have selected is silicon, so into an intrinsic silicon, we are adding pentavalent impurities. The resultant semiconductor is what we call as a N-type semiconductor. The resultant semiconductor is what we call as a N-type semiconductor. Now we are just taking an example here. It is not necessary that after doping it is going to be something like this. It is only for understanding that we are introducing something like this. Okay, the two-dimensional crystal lattice structure. Generally we have a three-dimensional structure, but here for understanding we are considering a two-dimensional crystal lattice structure after doping with it of a pentavalent impurities. Now for example, this is how it is going to look like. So all the blue that you can see here are nothing but, okay, your dopant or impurity atoms that we have introduced. And because I have already told you that we are having an N-type semiconductor, and that is the reason why we have introduced a nitrogen, which is a pentavalent impurity. And we know that pentavalent simply means that it is going to have 5 electrons. So if you can see here, 1, 2, 3, 4, 5, it is going to have 5 valence electrons, okay, in its valence orbit. So generally silicon is going to have 4 valence electrons. Okay, nitrogen has 5 and silicon is going to have 4 because it is a 4a group element. Okay, so it is going to have a 4 electrons in its valence orbit, and generally we know that when we have learned about the intrinsic semiconductors, we have discussed that. So in the case of a silicon, it is going to form 4 covalent bonds with the neighboring silicon atoms. Okay, so each and every silicon atom is going to share the electrons with the neighboring silicon atoms in its pure state, so that each and every silicon atom is going to be surrounded by 4 silicon atoms and it is bounded by the covalent bond. And we have also discussed that when you are giving some excitation, it can be an optical excitation or it can be a thermal excitation or any type of excitation. So whenever you are exciting it, then what is going to happen? When you are exciting it, the bond is going to break and thereby it is going to create the charge carrier pair. Okay, so when every covalent bond is going to break, it is going to generate electron hole pair. Now because you have introduced an impurity which is nothing but nitrogen into a silicon, now it is going to be a little bit different because each and every nitrogen atom is going to have 5 electrons rather than having 4 valence electrons. Now game is going to be slightly different. So here you can see the blue atoms are nothing but the pentavalent impurities, which are nothing but nitrogen in this particular case. So let us consider this is how your crystal lattice structure is going to look like at T is equal to 0 Kelvin. So if you closely observe, even a nitrogen atom is going to have 4 covalent bonds shared with that of neighboring silicon atoms. Okay, each and every nitrogen is sharing 4 covalent bonds. Okay, it is forming the 4 covalent bonds with the neighboring silicon atoms. Thereby, it is sharing electrons with the of silicon atoms. Okay, but there is one electron which is not going to be involved in any covalent bond. That is what we call as a loosely bounded electron. This electron is very much a part of a nitrogen atom, but it is not going to form any bond with that of a neighboring atoms. So we can call it as a loosely bounded electron to that of a nitrogen. Okay. So ultimately our aim is that this electron is going to be excited, so that electron, after excitation, the nitrogen is going to lose a particular electron, and this particular electron is what is going to be called as a free electron or a conducting electron. Okay, so to understand that particular concept, we are going to draw an energy band diagram so that it becomes very simple to us to understand the concept of extrinsic semiconductors. So in parallel with the crystal lattice structure that we have drawn here at T is equal to 0 Kelvin, now we are going to also draw the energy band diagram, which will give us a clear picture of what is actually going to happen. So let me have an energy band diagram. So now this band is what we call as a valence band, and this band we call as a conduction band. The minimum energy level of the conduction band is what we call as a EC, and the maximum energy level of the valence band is what we call as a EV. Now let us consider that the valence electrons which are present everywhere here, the valence electrons which are present in the valence band, and they are arranging themselves according to the amount of energy they have. So whatever electrons which are present here are those electrons which are present in covalent bond. If you observe here, all these electrons are nothing but valence electrons. All these electrons are nothing but valence electrons. But those electrons which are forming the covalent bond with the neighboring atoms, those are the electrons which are present in the valence band. And we know that here there are some electrons. If you observe here, each and every nitrogen is going to have one extra electron because it by default has the 5 valence electrons. But of course only 4 of them are going to involve inside the bonding, which is a covalent bonding. But the remaining electron, the one electron that we have, is actually loosely bonded to the nitrogen, but it is not going to form any covalent bond. So that electron, because it is loosely bonded and it is also ready to lose itself, okay, it is trying to come outside provided it has the energy, or someone supply some energy so that it can come outside very easily when compared to that of the other electrons. Because the other electron, the 4 electrons which are present in the silicon, or the 4 electrons which are present to the nitrogen, apart from the 5th electron, because they are present in the covalent bond, it is little bit difficult for them to come outside because they are present in the covalent bond. Okay, if it wants to come outside, it has to break the bond, for which it should have a significant amount of energy, and that energy is what we call as the energy gap. Okay, so each and every electron is present in a bond, the covalent bond. So if it breaks the bond, it requires the energy which is equal to the energy gap, so that it can jump from the valence band to the conduction band. But that is not the case with the 5th valence electron. Okay, so this particular 5th valence electron, because it is loosely bonded to a particular nitrogen atom, and also I can say that it requires a very less amount of energy so that it can come outside. So in order to visually show that it requires only very less amount of energy to become a conducting electron or a free electron, so those electrons are drawn in a particular energy level. Okay, those 5th electrons of the nitrogen are going to occupy an energy level. Why it is occupying here, why not here? The answer is very simple. Because if you draw here, it means that it also requires energy equal to energy gap to come outside. But that is not the case, right? The case is that it requires a very less amount of energy so that it can come out of the nitrogen and it can contribute to the conductivity of a particular material. Okay, so because it requires a very less amount of energy, so I am drawing it very near to the top of the conduction band. Now to make it clear that it only requires a very less amount of energy so that it can jump into the conduction band. So this energy level is what we call as a donor energy level. Why we are calling it as a donor energy level? The reason is very simple, because the nitrogen atom, or in fact each and every pentavalent impurity, when you are doping into the silicon, it is going to form an N-type material. Now what is the meaning of N-type? Electrons are going to be the majority carriers. How electrons are going to be majority? It is because each and every impurity that you are doping has a potential to donate one electron. So because it has a potential to donate one electron, we call it as a donor. Okay, so all the electrons which can be donated by a particular pentavalent impurity, those are going to occupy a particular energy level which is close to that of a conduction band. Okay, so we are drawing here and we call it as a donor energy level. Okay, now at T is equal to 0 Kelvin, do we have any free electron? Do we have any electron which can conduct? Is it possible for any of these particular electrons to actually participate in conduction process? The answer is no, because all these electrons are present in the conduction, are present in the covalent bond, and once they are present in covalent bond, they are not going to participate in the conductivity process. And what about the fifth electron? Fifth electron is not present in the any covalent bond. So why not? It can conduct, because it cannot conduct it. The reason is very simple, because it is part of a nitrogen, and when it is a part of a nitrogen, it is still present inside the nitrogen. It is not coming outside for conducting. It is loosely bounded, that is what we can say, but it is not ready to conduct. Okay, so I can say that at T is equal to 0 Kelvin, at absolute 0 Kelvin, there is no conductivity for this particular material. If you are applying a potential difference, the amount of current will be equal to 0, because there is no electron which is ready to conduct. Only when the electrons are ready to conduct, you can actually have a current inside the material. That is not possible as of now. Now, to make that happen, we can increase the temperature. And for example, now I am going to increase the temperature above 0 Kelvin. So as temperature increases above the 0 Kelvin, what is going to happen? You are providing thermal excitation. You are providing an energy in the form of temperature, right? So you are providing thermal excitation. Now once the thermal excitation is going to happen, slowly the electron which is loosely bonded to a nitrogen is now going to disassociate from its parent, and it is going to become a free electron. Now what is the meaning of a free electron? The meaning is that it is now ready for conduction process. So now when the electron disassociates from the parent atom, now this electron is going to be a free electron or a conducting electron. We can call it as a free or a conducting electron. Now here the same concept can be explained using the energy band diagram by saying that as the temperature increases, the electron is going to move from the donor energy level into the conduction band. The same process, whatever is happening here inside the crystal lattice structure, I can show in the energy band diagram to make it very simple. That the electron which is present in a donor energy level, now because of the thermal excitation, what is happening here? It is going to jump into a conduction level. It's nothing but a higher energy level which can produce the conductivity inside the particular material. So now an electron is jumping from a donor energy level into the conduction band. Now as the temperature increases, more and more electrons are going to get excited from the donor energy level into the conduction band. So the electrons are going to get excited from the donor energy level into the conduction band. Now this particular process of an electron moving from donor energy level into the conduction band is what we call as a donor level ionization. We call it as a donor level ionization. Now what is the meaning of this one? Donor level ionization. The donor level ionization means an atom is becoming ion. What is that atom which is becoming ion? It is a nitrogen atom which is becoming ion. Why? Because we can easily see here that nitrogen is losing an electron which is loosely bonded to it. Right? So when an atom is going to lose an electron, we call the particular process as ionization. And because a donor energy level is losing an electron, we call it as a donor level ionization. We call it as a donor level ionization. So this particular process of an electron moving from donor level into the conduction band is what we call as a donor level ionization. So this is going to happen. So the donor level ionization is going to happen inside a particular material. Right? So slowly as the temperature increases, if you increase more and more temperature, more and more number of electrons are going to move from the donor energy level into the conduction band. And after some time, you can observe that this energy level is going to become completely empty. The donor energy levels which are present here are going to become completely empty. It is because of the simple reason that the electrons are going to move from the donor energy level into the conduction band. And don't think that the electrons are not going to move now from valence band to conduction band. There will be some number of electrons which can have the energy which is equal to energy gap. When they attain that much amount of energy, they can also move from valence band to the conduction band. So when an electron is moving from valence band to the conduction band, it is going to leave a particular space. The space is what we call as a hole. So here also I can describe it by saying that by breaking the covalent bond, when you are providing an energy which is equal to energy gap, it is going to break the covalent bond. Now the electron is going to become free. So the space that is left is what we call as a hole. So you can see that here there are huge number of electrons which are possible. Yes. Now we can also see that this energy level is going to be completely empty. Now when it is completely empty, we can call it as a full dopant ionization. Now what is the meaning of a full dopant ionization is that all the dopants or the impurities, which are nothing but nitrogen atoms here, whatever you have introduced, now all of them have become ionized. Each and every nitrogen atom has contributed to an electron because of the process of ionization. That is what we call as a full dopant ionization. Now after full dopant ionization, now because there are no electrons which are present in the donor energy level, now you cannot expect the conductivity to increase. Yes or no? Because now the energy level is completely vacant. Now no more electron can move from a valence from the donor energy level into the conduction band. But one thing can happen, that the electrons from the valence band can move into the conduction band because there are huge amount of valence electrons are present. So they can move. But here it is not possible for an electrons to move from the donor energy level into the conduction band after completing the full dopant ionization. Okay, so this is the concept of N-type semiconductors. Okay, so what we have started with, first of all we have started with what we learning about an extrinsic type of semiconductor, which is nothing but a impure type of semiconductor. Okay, we can have two types of impure semiconductor, which is extrinsic semiconductors. One is N-type, the other is P-type. So N-type is resulted when you are adding a pentavalent impurities or fifth group elements. So thereby, as a result, you are going to have a material where the electrons are going to dominate over that of holes. Did it happen? You can see here that the number of holes are very less when compared to the number of electrons. You have to remember, you have to understand that when I am saying the electrons are majority, I am talking about the conducting electrons, not the valence electron. There are huge number of valence electrons, but those are not going to be active for the conductive process. So the electrons or the free electrons are going to dominate over the holes. Holes are always present in the valence band. Okay, so if I want to show the substrate, okay, the notes will be given to you, provided to you below the lecture, so you can download it. Now if it is an N-type semiconductor, now generally an N-type semiconductor is represented with the dopant atoms which are ionized. Just now I told you that the nitrogen atoms are going to be ionized. So why am I representing a positive ion here? Because all the impurities, which are nothing but the pentavalent impurities, when you are removing an electron from it, the pentavalent electron is removed. When the fifth electron is removed, it means that it is going to become an ion. Now because it is losing an electron, every time when an atom is going to lose an electron, it is going to become a positive ion. Now the electron that it is going to lose is nothing but a free electron now. This electron which is present here is now ready to move. This picture clearly indicates that each and every donor ion is actually contributing one electron each, and that particular electron is represented here. And there will be some electrons which are generated because of movement from valence band to conduction band. Okay, so in that particular process, you can have an electron hole pairs. So this is how you are going to represent a N-type semiconductor. This is how we can represent a N-type semiconductor. I hope it is clear. Now we are going to move on to discuss about a P-type semiconductor, and the process is going to be almost same. Okay, there is not going to be great amount of difference between the N-type semiconductor and the P-type semiconductor, except that here the material or the impurity that you are going to introduce is going to be a trivalent impurity, or it's going to have only 3 electrons in its valence band. That is the difference. Here the nitrogen atom, which is a pentavalent impurity, has 5 electrons. So because it has 5 electrons, it is contributing 1 electron each. Now the thing is, the scenario is completely opposite. That now a trivalent impurity is only going to have 3 electrons. Now let us see that particular case. So now we are going to discuss about a P-type semiconductor. So initially, let us discuss about the condition of T is equal to 0 Kelvin. Okay, and we know that the trivalent impurity, one of the example is nothing but boron. Now exactly the same places out of nitrogen, I have introduced boron here. Okay, boron is a trivalent impurity. So a boron is going to have only 3 valence electrons, and all the 3 valence electrons are going to contribute or going to involve in the process of covalent bond. Okay, each and every boron is going to form 3 covalent bonds. Each and every boron is going to form 3 covalent bonds. And you can see here that it does not have the 4th electron, the 4th valence electron. Thereby, there is no bondage, even though a silicon is going to have an extra electron. Because silicon has 4 electrons, but the boron is only forming 3 covalent bonds. So wherever you have a boron, it is only going to form 3 covalent bonds, whereas silicon has an ability to form one more covalent bond because it has an extra electron. If you observe here, now the boron, how many electrons it is going to have? If you observe, it has a 3 valence electron and it is forming 3 bonds. It means that total it is going to have 6 valence electron. Now if it can manage one more electron, then it means that it can form a bond. Now when it forms a bond, it means that in its valency it is going to have 8 electrons. Okay, 3 of its own and 4 of the silicon and 1 it is getting from outside. That is why a boron has a tendency or an affinity to accept an electron. Because when it accepts an electron, think here that for example if it accepts an electron, what is happening here? When it accepts an electron, now it can form the 4th bond. Now when it forms the 4 bonds, it is going to be stable because it is going to have 8 electrons. The total 4 of its own and 4 of the silicon. Okay, so it can have 8 electrons in its valency, which is nothing but a stable state. Whenever a particular atom, okay, either it can be through transfer of electrons or it can be through the sharing of electrons. If it is able to manage 8 electrons, then definitely it is going to have a stability. And each and every atom tries to attain stability. That is not a difficult thing to understand. That is a very basic concept of an atom. So here the thing is that now boron always looks for one electron, one extra electron. So similarly, whatever I have explained here, I am going to draw in an energy band diagram. The simple reason for drawing an energy band diagram is because it is going to make the concept extremely simple. Now, the electrons which are present in the valence band are nothing but those electrons which are participating in the covalent bond. What do you think? That because an electron is not present here, can I represent a hole here? Is it possible to represent a hole? Because if I don't have an electron in a particular place, generally we represent with a hole. So using that particular concept, can I represent a hole over here? Answer is no. Why cannot we represent? It is just a vacancy. You don't have a place. Okay, you don't have an electron over here. But it is not created because of an electron moving from valence band to conduction band. You should always remember that whenever there is a hole generation or a hole creation, it is only because of an electron moving from valence band to the conduction band. Or it is moving from a ground state to an excited state. I can say like this, that whenever a hole is formed, it is only because of an electron moving from a ground state to an excited state. But here it is not the case, because an electron is by default not present, because boron is only going to have 3 valence electrons. That is why the fourth state is empty. But that doesn't mean that you should have a hole over here. Okay? The hole is not present because there is no electron which is moving from a ground state to an excited state. That is not happening at all. That is why there is no representation of a hole. That is just a vacancy which is ready to accept an electron. That is true, but it cannot be represented with a hole because hole has a completely different concept. Now, this is the scenario at T is equal to 0 Kelvin. Now, in order to also imbibe the concept of boron having an affinity to accept an electron, so that level is to be drawn very close to the top of the valence band, and we call that particular energy level as the acceptor energy level. Just like the way we have represented a donor energy level, similarly here we are calling as an acceptor energy level. Now if you see here, a donor energy level was drawn close to the top of a conduction band, whereas the acceptor energy level is drawn close to the top of a valence band. Now acceptor energy level is drawn for a very basic reason, that a boron is having an affinity to accept an electron. So whatever electron that particular boron is going to get inside, that is going to be present in the acceptor energy level. You could get a doubt that why are we drawing the acceptor energy level very close to the valence band? Why not in the middle, or why not near the conduction band just like the donor energy level? The reason is because only these electrons which are present in the valence band, those are going to move into the acceptor energy level. But they are not going to go if you are not going to provide any energy. You have to supply some amount of energy, not high amount of energy. For example, if it requires good amount of energy, it means that it is moving from valence band to conduction band. But here it only requires some amount of excitation so that it can move from the valence band into the acceptor energy level. It simply means that electron is moving from a particular bonds into the boron. Okay, so this particular acceptor energy level is ready to accept an electron. Now let us increase the temperature to see the process. So as temperature increases, okay, as the temperature increases, what happens? The electrons which are present in the silicon atom, they are going to gain an electron, they are going to gain the energy, and they are going to move near the boron. Why? Because the valence electrons are gaining the energy. When they gain an energy, they try to move into the advanced energy level. Now what is the what is the nearest advanced energy level that is possible? The nearest advanced energy level that is possible is nothing but an acceptor energy level. Because it's a vacant level which is available. See, if I don't have this particular level, it means that there is no vacant state that is available in the middle in the energy gap. Inside the energy gap, there is no energy level is present. if I wipe out this particular acceptor energy level, because an acceptor energy level is present, it means that there is an extra energy level. So every electron which is gaining an energy, that with having sufficient amount of energy, it can move into the acceptor energy level. That is the meaning of moving an electron from the valence band or to the silicon to the boron. Now it is going to form a bond here. It is going to generate a hole here. I can represent the same over here. When the electron tries to move into the acceptor energy level, thereby it is going to form a hole. Similarly, it can also happen something like this. That an electron is going to move near the boron and it is going to form a bond here. Similarly, an electron can move to the boron. Okay? So that is what is happening here. The electron tries to move into the acceptor energy level. So thereby it is going to create a hole. Now you can see that the holes are created because then electrons are moving from the ground state to the excited state. Acceptor energy level is one of the excited state. Some of the electrons are going to move from the valence band to the conduction band. Some electrons are going to move from the valence band to the conduction band. Okay, so whenever an electron is going to move into the acceptor energy level, we call the process as acceptor level ionization, just like the way we have discussed about donor level ionization. So here we are going to discuss about acceptor level ionization. Okay, so whenever an electron is going to move from the ground state to the acceptor energy level, valence band to an acceptor energy level, we can call it as a acceptor level ionization. As the temperature increases, acceptor level ionization is going to increase and more amount of holes are generated inside the valence band. Holes are nothing but the positive charges. Okay, we are going to treat the holes as the positive charges inside the semiconductors. As temperature increases, more and more holes are going to be created because more and more electrons are going to be introduced into the acceptor energy level. After some amount of time, okay, as particular process is going to increase, it means that as the temperature increases, more and more number of holes are going to be generated inside the valence band. This is going to happen till the acceptor energy level is completely filled. Okay, just like the way the donor energy level was completely vacant in the last case, here the acceptor energy level is also going to become completely filled. That is what we call as a full dopant ionization. Okay, so because the electrons are actually, because the impurities which are nothing but boron atoms are accepting an electron, we call it as an acceptor. Correct? So it has each and every acceptor impurity can accept only one electron. So thereby there is a limit that it cannot accept all the electrons that particular valence band is supplying. There is a limit. And when the limit is reached, that is what we call as a full dopant ionization. After that, if it wants to move, it can only move into the conduction band. Okay, thereby generating an electron hole pairs. That is possible. But now it is not, after reaching the full dopant ionization, it is not possible to enter into the acceptor energy level. Okay, now this particular, the same thing can be represented using a strip of a P-type semiconductor. So now I am going to represent the negative ions because the acceptor is basically acceptor atom, which is nothing but a boron atom, is accepting an extra electron. So when it accepts an extra electron, it is going to become an ion which is a negative in nature. And I am going to represent each and every negative ion with a hole in order to indicate that it is because of each and every acceptor atom accepting an electron, it is going to create a hole somewhere else. So each and every acceptor is going to create a hole to represent that one. I'm going to create a hole or associate a hole with the acceptor ion. Now some holes and electrons are generated because of the breakage of the covalent bonds. So this is nothing but our P-type semiconductor. This is nothing but P-type semiconductor. So students, we have learned about both N-type semiconductor and P-type semiconductor, how they are generated. We have also learned about full dopant ionization. Generally the full dopant ionization is going to happen around the temperature which is room temperature. Okay, as the temperature reaches the room temperature, generally the full dopant ionization is going to complete. Now let us discuss about a concept which is called as charge neutrality, which is a very important concept. So in order to understand the concept of charge neutrality, what I am going to do is that a particular intrinsic silicon substrate is going to be doped with both N-type and P-type impurities. I am going to dope the intrinsic material with it of both N-type and P-type impurity. Probably after doping it is going to be something like this. Minus, minus, minus. Now what is the meaning of minus? Minus means negative acceptor ion. And plus, plus, plus. Minus, 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 minus. Plus, plus, plus. Again minus, minus, minus. And again plus, plus. And we know that each and every acceptor is going to be associated with a hole. And each and every donor impurity, which is nothing but a donor ion here, is going to be associated with the electron. So under the thermal equilibrium, the scenario is going to be something like this. And some of the electrons are going to be generated because of the breakage of the covalent bonds. Okay. Now this is the type of material that I am going to have after I am going to dope with both N-type and P-type impurities. Now what charge neutrality says is that, it's very simple concept. What charge neutrality says is that the positive charge inside a particular material will be equal to the negative charge. Okay? If the substrate completely is isolated, the positive charge inside it will be equal to the negative charge. That is what the charge neutrality says. Positive charge is equal to that of a negative charge. Positive charge is equal to that of the negative charge. Now what is the positive charge inside it? Hole and also the positive ions. The positive ions are nothing but donor impurities. So I am going to represent with Nd. Or if you want to represent it in ionized form, you can write it as Nd plus. So this is the total positive charge I can have inside a particular material. It's nothing but the number of holes that are available plus the number of donor ions that are available, because donor ions are also positive charge. It will be equal to N, which is the number of electrons that are available plus the acceptor ions. This is always going to be valid. This is what we call as the charge neutrality. This is a charge neutrality condition. Now what happens in the case of N-type semiconductor? When you want to form an N-type semiconductor, it means that you are not going to dope with it of acceptor impurity. So Na will be equal to 0. When you are having an N-type semiconductor, it means that you are not going to dope with it of acceptor impurity, you are only going to dope with it of donor impurity. So Na is equal to 0. If you put that one, in that case the value of N will be equal to that of P plus Nd plus. Similarly, in the case of a P-type, Nd is equal to 0. So therefore, the value of P is equal to N plus Na minus. Okay? We can just take an approximation that whenever the doping levels are more than a moderate level, then the value of N is going to dominate over the value of P. then I can simply write the value of N is almost equal to the value of Nd. And similarly, when the doping is on the higher side, then I can say the value of P is going to dominate over that of N. So the value of P can mathematically be written as equal to that of N. Okay, we can take this particular assumption only in the case where the value of Nd, the doping, is going to be higher when compared to the intrinsic concentration. Then only we can say that the doping levels are higher, so that I can take this particular condition, either this one or this one. We can consider only when the doping level is higher than the Ni. What is Ni? Ni is nothing but intrinsic carrier concentration. Okay, so for an intrinsic semiconductor at a particular temperature under thermal equilibrium, the number of electron holes that are available. Why they are available? It is because of the breakage of the covalent bond that happens with the temperature. So number of electron hole pairs that are available inside an intrinsic material at a particular temperature under thermal equilibrium is what we call as the intrinsic carrier concentration. So when the value of the doping is higher when compared to that of Ni, or Na is going to be higher when talking about a p-type material, when the value of Na is going to be much higher when compared to the value of Ni, I can take this particular approximation of writing the value of P is almost equal to the value of N. Now, considering that, okay, let me consider that I'm having a p-type, n-type material, for example. I'm having an n-type material and have satisfied the condition that the doping level is such that the value of Nd is much higher when compared to the value of Ni. If that is the case, then I can say that the value of N is almost equal to the value of Nd. Okay, very happy. Then how can I calculate the value of P? The question is that, okay, I have doped with the condition that value of Nd is much higher when compared to the value of Ni. That is okay. So I can say that the value of N is almost equal to the value of Nd. Okay, accepted. Now how can I calculate the value of P? Okay, to calculate the value of P, which is nothing but minority carriers. Okay, for an n-type material, P is nothing but a minority carriers. N are a majority carriers. So in order to calculate the value of P, I am going to use a particular law, is what we call as the mass action law. It's a very, very important law. Now what mass action law says is that under thermal equilibrium, the product of electron and hole concentration is constant and is equal to the square of the intrinsic carrier concentration. What does it say? That for any type of material, semiconductor, okay, it can be an intrinsic material or it can be an extrinsic material. The condition it is going to satisfy is that the value of electron product hole concentration, when you are multiplying both electron and hole concentrations, it will be equal to that of Ni square. Ni is a constant intrinsic carrier concentration at a particular temperature. Okay, so I repeat once again, under thermal equilibrium, the product of concentration of electrons and holes is constant and it is equal to the square of the intrinsic carrier concentration at that particular temperature. That is what we call as a mass action law. Now why are we going to use a mass action law? Because we are clear that the value of N is equal to Nd in the case of an n-type material which is sufficiently doped. In that case, I can calculate the value of P by simply writing Ni square divided by N. What is N here? Nd. So therefore I can calculate the minority carrier concentration also using the mass action law. So many a times in GATE and also in engineering services, the question is directly asked based on the concept of mass action law. Let us write the question on it. It's a very simple question that has been asked in GATE 2014. This question has been from GATE 14. A silicon bar is doped with the donor impurities with Nd is equal to 2.25 into 10 power 15 atoms per centimeter cube. Given the intrinsic carrier concentration is equal to 1.5 into 10 power 10 electron hole per centimeter cube at room temperature T is equal to 300 Kelvin. Assuming full dopant ionization, the equilibrium concentration of electrons or holes respectively are dash. See, what is the meaning of equilibrium? Generally, we make sure that that there is no variation in the temperature, okay, and the experiment is done keeping the temperature is going to be same everywhere. There is no change in temperature at any point in a particular substrate. That is the meaning of thermal equilibrium. We have to make sure that there is no change in temperature at all, and each and every point of a particular material is present at the same temperature. There is no change in the temperature. That is meaning of equilibrium. Okay, so what is the meaning of full dopant ionization? We have already seen that each and every donor, right? So each and every donor has actually get ionized. So thereby it has donated 1 electron each. So whatever the number of donor atoms that we are going to have, that many number of electrons we are going to have. That many number of donor electrons are going to be provided by the donor atom, because here it is given that the full dopant ionization is over. We know that the value of Ni is given as equal to 1.5 to 10 power 10. So the value of Nd, you can see here, is much higher when compared to the value of Ni. So when that happens, I can simply write the value of N is almost equal to the value of Nd. So it is very clear the value of N should almost be equal to the value of Nd. Correct? Now once you have the value of Nd or N is equal to this one, what should be the value of P? The value of P is going to be Ni square divided by that of Nd. So Ni is 1.5 into 10 power 10 whole square is going to be 2.25 into 10 power 20 divided by 2.25 into 10 power 15. So it is simply equal to 10 power 5. So a donor type impurity is added extent of 1 atom per 10 power 8 silicon atoms. The value of resistivity is dash. Okay. One thing that you have to do is that you have to know the formula for resistivity that we have seen in the last class, right? So in the case of resistivity, it's nothing but 1 by conductivity, and conductivity is nothing but 1 by the electron conductivity plus the hole conductivity. Okay, and the second thing is that here the doping level is given. It is nothing but 1 is to 10 power 8, and we know that the total number of silicon atoms that we have is 5 into 10 power 22 atoms per centimeter cube, which implies that the value of N-type impurity, right? So the value of Nd, because the ratio has to be 1 is to 10 power 8 divided by 10 power 8, something but 5 into 10 power 14. So this is the value of Nd. Clearly you can see that the value of Nd is much higher when compared to the value of Ni. Generally the value of Ni is going to be equal to the of 1.5 to 10 power 10 at electron hole a centimeter cube in the case of a silicon. It is much higher when compared, Nd is much higher when compared to that of Ni. So the value of N is almost equal to the value of Nd. And the value of P is going to be much lesser when compared to the value of N. So we can remove this one completely. So I can write it directly equal to 1 by Nd Q mu. Okay, so we can assume that the value of mu n, the standard value in the case of silicon, is going to be 1300. Okay, centimeter square per volt second is the value of mu n, and you can calculate Nd is given. Okay, we have found the value of Nd. Q is going to be 1.6 into 10 power minus 19, and mu n is equal to 1300. And you can calculate the value, and you can tick mark on any of the possible answer. Okay, so with this we conclude the topic on extrinsic semiconductor. Hope it is very useful. Okay, all the very best to you all guys.